Okay, so it is already time, I think. Now, where is the Dr. Tanasit? Dr. Tanasit, are you here? I think I cannot see anyone.
Tanasi is a co-chair, right?
Yeah, you are the chair, so you co-chair usually present you, and then you can start, and after that you can take over the chairing the session.
Okay.
So that was the plan.
So you are my chairman. I know.
Arun, we need to start this session. Is it okay?
Okay. Okay.
All right. I think let's go to start.
Mm-hmm.
So welcome to our afternoon session. And our keynote speaker in this session is Dr. Yan Hui from the Beijing University of Science and Technology, Beijing, and she will be giving your talk. And she is also chair of the session. So as she is presenting, so I'm just helping this session. And once she will complete her presentation, she will take over the chairmanship of the session. So Professor Yan Hui, please you start your presentation, and also you give little bit of brief about you so that our participant can hear from you. Okay, about yourself and also about your university, and then you can start your topic. Thank you. Please.
Okay. Okay. Thank you, Professor Firoz. Thank you. Thank you for your introduction. Okay, I will give a brief introduction of myself and my school. Okay, I worked in the School of Energy and Environmental School in University of Science and Technology, Beijing. Yeah, it's Beijing. You're welcome to Beijing if you have a chance. Okay, but okay, and today I would like to give some speech about heat conduction in carbon nanotube assembled structures. But we also do some research on heat storage. It's related with nanomaterials and nano with energy. Anything, okay? But no, not anything. Okay, something. Okay, yeah. Okay. Can I begin our presentation now? Okay. I will show my screen.
You share your screen and you can start.
Okay. Okay. Good afternoon, everyone. It's my honor to be here to give a speech. My paper title, my presentation title is Enhancement of Heat Conduction in Carbon Nanotube Assembled Structures. Electron and phonon transport of carbon nanotubes has attracted much attention in the field of nanoenergy and nanoelectronics due to its ability to facilitate heat dissipation and electrical transmission and compatibility with various nanometer size devices. However, once assembled, such as into bundles, fibers, and fumes for practical application, CNT tubes exhibit considerable performance deterioration due to the phonoscattering, phonomode squench, electro-hopping barriers, and the numerous intertube interfacial structures acting as energy transport barriers. That is, the bulk electrical and thermal conductivities of CNT ensembles typical example is CNT fiber. It has one order of magnitude reduction in both electrical and thermal conductivities. This clearly retards efficient application of tubes. So developing new strategy to improve the interfacial thermal and electrical transport is critical for solving the drawback. We can use nano units filled in tube or decorated outer tube fiber as a promising material platform, such as inner and outer tube functionalization, non-bonded inner tube loading, non-covalent outer tube functionalization, and so on. It has been confirmed that adding nanoparticles such as gold nanoparticle, nanocrystals, or nanoclusters, iodine molecules, the red color material is our focus, can greatly evaluate the electron transport. However, whether it can also promote heat conduction within the tube or interfacial transport, the underlying mechanism. That's what I do. Okay. Various materials such as fluorine metals or even proteins have been introduced into CNT cavities. Of course, experimental preparation is still difficult to achieve. This table gives some inner tube functionalization. In tube filler includes what I have mentioned. Yeah, okay, fluorine, okay, silicon nanoparticles. Table gives some outer tube decoration, such as gold nanoparticles, iodine doping. Okay, but most studies focus on the electrical conductivities of assembled structures, but not the thermal properties. In this talk, our material platform is adding zero-dimensional spherical fluorine molecules and one-dimensional gold nanowires into the tube. On the other hand, decorating gold metal nanoparticles and non-metallic iodine nanotrends into the CNT fiber. It is out of the tube into a tube. That is, we have 4 kinds of assembled structures. The contribution of nano units to thermal, not electrical transport is our main concern. The first 2 kinds assembled structures are studied by molecular dynamic simulation due to difficulty. The last 2 are studied experimentally and theoretically. Okay. First, let's go to 2 interesting structures. That is heat conduction in filled carbon nanotubes. The first is carbon nanopiped carbon nanotube filled with spherical carbon-60 fluorine molecules. Carbon-60 represent peace and the tube representing a port. Nanocables, the composite of CNT filled with nanowire is called nanocable. Here the filler is gold nanowire. The tube represents the insulating shell and the nanowire represent conducting wire. The nanowire filled in tube exhibit multi-shell packs consisting of coaxial cylindrical shell. Based on carbon nanopiped and nanocables, these 2 models, we employed molecular dynamics calculate thermal conductivity. The results shows that the filled carbon-60 can increase thermal conductivity up to 9.6 times, a huge enhancement. Just like people, the filled nanowire can also increase the thermal conductivity, not so much increase like carbon-60 filling, because gold carbon are of heterogeneous atoms. We further analyze this by local heat flux and the relative distribution of different phono oscillation frequency and so on. Compared with bare tube, Carbonyl P-port has more non-uniform local heat flux over the tube wall region. And the high local heat flux, which is represented by red dots, mostly concentrated in carbon-60 region, indicating that the contribution of carbon-60 molecule is more than tube wall atoms. Furthermore, the heat transfer in tube wall region appears to be at a higher heat flux than bare tube. That means the heat conduction ability of tube wall atoms is improved by carbon-60 loading. From these slides, it is shown that the thermal conductivity of bare tube, the left picture, and nano P-port, the right picture, both they are dominated by low frequency phonos, less than 20 THz. And with filling, the assembled structure has more low frequency phonos than bare tube. It can up to 97%. That is, carbon-60 filling induce low frequency phono increase. I would like to give more details with VDOS, vibrational density of states. We know that carbon nanotube have 5 eigenvectors with carbon-60 filling, since both the tube and the fillers are of carbon atoms. There is small vibrational mismatch, that is intrinsic high-level matching of VDOS between filler and the tube. We can see that the coupling of LFP, low frequency phono modes, less than 20 THz, between the tube and filler is partially covering XY direction transverse acoustic modes and ratio breadth. We know that carbon tubes have ratio breadth mode, just like V breadth, okay, are primarily responsible for the increment of thermal conductivity. With gold filler, besides the increment of low frequency phono, also impacts the thermal conductivity favorably. The high frequency VDOS, okay, we can see that also increase, further contributing to the enhancement in heat conduction. Interestingly, we found that the motion of filler also contribute to heat transfer enhancement. This angular velocity picture indicates that carbon-60 has random rotation in all 3 directions, no matter what the filling ratio is. The action of each carbon-60 molecules is recorded in this picture. In a full-filled tube, this picture and this picture, we can see that carbon-60 molecules remain in their original position. However, once not fulfilled, carbon-60 could have translational movement, that is, access of tube. As the filling ratio is larger than 50%, interestingly, the translation motion of carbon-60 molecules gets more and more restricted with increasing filling ratio. Accordingly, the enhancement of mass transfer contribution to total heat transfer relative to bare tube in this picture get from our calculated result. Also, first increase up to maximum 30% at a filling ratio of 50%, then falls with restriction of actual translational motion of carbon-60 molecules. This also can explain why semiconductivity curve changes like this. That is, with a boosted and then restricted motion of carbon-60, semiconductivity first increase and then decrease with rising filling ratio. For that semiconductivity could be precisely modulated by filling ratio dependent movement of carbon-60. Let's compare nano-P port with nano cables. We consider for nano-P port, since there is small vibrational mismatch between carbon-60 and the tube, we can have energy. Blue shadow in this picture, since there is a small vibrational mismatch between them, so mass transfer become the dominant factor. That is, with increased filling ratio, the semiconductivity increase first with boosted motion of carbon-60 and then decrease with restricted motion of carbon-60. It's non-monotonic dependence on the filling ratio. Different from nano-P port, the semiconductivity of nano cables always increase with the increased filling ratio, primarily because the contact area between gold nanoparticle and the tube enlarges. That is, gold nano Y, sorry, not a particle, gold nano Y. Tube mismatch dominates, enabling the contribution of enlarged contact area outweighs the reduction from restricted mass transfer. Of course, similar to the P port, not fully filled, the filler nano Y, gold nano Y, would be in actual motion, which induce a mass transfer and increase the energy transportation. Let's go to the second decoration. It's intertube thermal transport of CMT fiber, intertube decoration. Vertical allied tube arrays was synthesized through chemical vapor deposition. Gold nanoparticle or iodine nanoparticles dip the fiber into the metallic salt solution or expose it to iodine vapor. We can see that from our test, introduce mind modification so that their pristine structures could be maintained. This is pristine CMT fiber. We can compare it with after decoration. After decoration, the intrinsic semiconductivity, we tested it by our homemade 3-omega technique. From the results, we see that after decoration, the intrinsic semiconductivity less than 2 millimeters gets improvement about 70%. Apparent and the intrinsic semiconductivity shows the quadratic length dependence owing to the radial heat loss through radiation. Similarly, for iodine decorated fiber, the intrinsic, this bar clearly shows that the intrinsic semiconductivity of iodine decorated CMT fibers achieve a noticeable increase up to 55%. The following is a Raman spectra for different CMT fibers. We use Raman spectra we use it to investigate the change of phono-vibrational modes of CMT fibers after decoration. Iodine molecules typically from charged I3, I5 chain, represented by two peaks in Raman spectrum. Blue shift to the right in peak positions after decoration reflects a slightly carbon-carbon bond shortening, that is phono-stiffening effect. We also can see after gold nanoparticle decoration, we obvious blue shift. Compare these two pictures occur in equivalent, that means an equivalent p-type doping effect, that is electrons was ejected from tubes and then used to reduce gold ions to gold atoms, that is electron transfer. And this results in weak bonding between gold and tubes. Some sp2 graphic plane-like carbon-carbon bonds transform to a certain and a weak sp3 diamond-like bond without affecting carbon nanotube structure. There is no real bond. And further examination of the frequency against laser excitation energy, declaration that gold decoration could retain high phono transport velocity, same as the group velocity of pure tube. That is a slight decoration of gold nanoparticle will not deteriorate the phono transport within the tubes. Furthermore, let's look at the sharp increase of normalized intensity of G peak. It reveals that a stronger electrophono coupling, that is electrons in gold and phonons in carbon atoms, and enable phonomode interface, possibly evaluating the interface transport. This boosted phono transport was further investigated by use molecular dynamic simulations. Interestingly, with increased gold nanoparticle amount, several interface conductance first increase up to a platon and then slightly reduce. We would deduce that the excess addition of gold could possibly deteriorate the gold-carbon interfacial phono transport and reduce the degree of boost. I would like to give more details with VDOS analysis. We can see that from total VDOS, gold nanoparticle induce low frequency phonos, just like the gold nano Y in tube, carbon 60 in tube, induce low frequency phono excitation in both tube and gold nanoparticle. And the increase of atomic ratio, gold to carbon atomic ratio, we can say that result to the increase of more low frequency phono. Since the LFP, low frequency phono, dominates the non-bonded thermal transport, the overall thermal conductivity would get boosted. Let's look at the local VDOS of interfacial carbon atoms. On heat source first. That is similar of decorated counterpart. On heatsink, great enhancement of LFP in the frequency range of 2 to 3.5 THz, consistent, agree with that of gold nanoparticle vibrations, suggesting more low-frequency phonon are excited by gold nanoparticle in resonance with vibration of gold nanoparticles. I would like to emphasize that gold nanoparticle redistribution LFP modes into the interfacial carbon atoms and activates a resonance of low frequency phonon between tube and gold nanoparticles. By MD simulation, we further attribute 3 modes mechanism to enhancement for iodine decorated fibers, 3-fold mechanisms. One is induce more low LFP, just like gold nanoparticle of the interfacial carbon atoms. Since the vibration of iodine atoms are concentrated around the extremely low frequency region, less than 2 THz, the interfacial carbon atoms on both carbon tube 1 and tube 2 tend to vibrate at lower frequency due to the interaction of iodine atoms. This is the first mechanism. The second mechanism is improving the matching level of VDOS at the intertube interface. We can check it by phonon overlap energy that represents the matching level. We can see that a boost of from 0 to 60 THz frequency range is a strong indicator of the remarkably enhanced heat transfer at the intertube interface. The next is iodine Chiang provides additional thermal transport trainers. We further calculate the interfacial heat flux originated from tube 1 and tube 2, and tube 1 to iodine filler interactions and their sum. This suggested that the CNT tube and iodine interactions indeed facilitate the interface transport, which also confirmed that iodine trains provide thermal transport trainers between tubes. Okay, finally, I would like to give a conclusion. For enhancement of heat conduction in carbon nanotube assembled structures, we get it by adding carbon-60 gold nano-Y into the hollow tube of tubes, or using fiber decorated with gold nano units lying in or out the tube. They introduce more low frequency phonon, LFP, vibration density of states, since LFP dominates non-bonded thermal transport. So the overall thermal conductivity in composite nanostructures would get boosted. Of course, other discussed factors, such as high level matching of VDOS, movement of filler, enlarged contact area, slide decoration, additional thermal transport channel are also beneficial to the enhancement of heat conduction. We expect our work would be a step for developing advanced CNT-based functional materials with high thermal transport. In addition, the exploration of new enhancement mechanism for thermal transport in CNT assemblies. Okay, that's almost all for my presentation.
Okay, thank you, Professor Yan Hui Feng. It's a very timely now. We are actually exactly on time. And Dr. Tanasit, are you here now? I saw your name there.
Yes, I'm
Ah,
here.
yeah, here, because we are looking for you. because Yan Hui and you are the chair and co-chair here. So actually, we thought that
we
you
share
will be...
together. Yeah. Okay.
So
Thank
we
you.
missed you, and that's why I filled your shoe. All right. So now we are running out of time. Is there anyone has any very urgent or burning question? You can ask maybe one question.
I'm sorry, maybe my presentation is a little longer. Okay, the time.
No, it's okay.
Yeah, okay.
Okay, because this topic is very interesting topic. You saw that there's a lot of parameters of thermodynamics parameter you need to enhance, and with this, what sort of depending on that you can enhance differently. Each of them has a different advantage. Explained to you is a very complicated thing, but it is a very vital thing for the future. So now with this comment, if there is no questions, so we thank Professor Yan Hui for her beautiful presentation. And now I request Professor Yan Hui and Dr. Tanasit to take over the session, and both Professor Yan Hui and Tanasit will continue your session. Thank you. So Yan Hui and Dr. Tanasit, floor is yours, and you continue ask other academics to present. And Professor Yan Hui, you can unshare your screen, then your next presenter can share the screen.
Okay. Professor Tanasit, I will stop my share screen. Okay.
Yes. Thank you. And I say goodbye to you.
Thank you, Professor Philos. Thank you.
Yeah, it is our pleasure to all of you to see here and your participation. Thank you.
Okay. Professor Tanazi.
Yeah.
Okay, I will choose the first three presentation, and would you last three?
Oh, it's me. Sorry. Can you hear me?
Yeah. Oh, yeah. I know. Okay. The first presentation is Doctor on three, right?
Yes.
Yeah. Please share your screen. Okay.
Okay.
Thank you.
A moment. Okay. Do you see my screen? Hello?
Yeah. It's okay.
Okay.
Clear. Okay, clear.
Okay. Good afternoon, everyone. My name's first of all on Sri. I am a postdoc fellow at Department of Mechanical Engineering, Chiang Mai University. Today, I am going to talk about promoting energy conservation in gas power defining of pork skin crackers with automatic control for small and micro size enterprises. In Thailand, food industry is the third. It has about 15% in the Thai manufacturing output. One of the most popular is pork skin cracker. it is a pork skin that is fried in a very hot oil. This is the figure of the pork skin cracker. Generally, this type of business is SME in Thailand. So they use a small technology in the production process. So people or the operators play the key role in all the process of the production. In the pork skin cracker production, these are the main thing. The first one is a pan used to fry the raw pork skin, and the second one is a heat source, in which usually from LPG combustion. So the operator control the heat by this valve. This is less accurate of the control, so the process consumes a lot of energy and has very low energy efficiency. So some products are damaged. So the objective of this work were to develop a cost-effective and energy efficient fire for processing pork skin crackers, and to demonstrate this proposed fire to Thai pork skin cracker SME. This is our fire design and layout. There are 4 main components. A moment, I cannot click. Okay. Okay, the first one is a heat exchanger, which is used to transform the heat from the LPG combustion to the oil. And the second one is oil pan, used to fry the pork skin, raw pork skin. And the third one is the LPG combustion chamber. And the last one is the oil temperature controller. This is the prototype of the controller that we apply from our previous work. Honestly, for more detail about the controller, please consider this DOI. But for the main idea, this is about using 2 valve controller. And this is the real fire, and this me dealing operating test. The developed fire sent to 14 sites in Thailand, and we train them about how to use our fire, and they record the data of LPG use for us. This is all the 14 sites that we visited. After using the fire for like almost 2 months, they said that they were satisfied with the operation and the quality of the product. Academically, by comparing the traditional one and what we developed, By the traditional fire or without the controller, the pork skin crackers normally take about 20 to 60 seconds to get done. And the frying oil temperature tend to drop when the raw pork skin put into the pan. So the operator would turn the LPG up to increase the heat input. By our developed fryer, the frying oil temperature was better stabilized at the desired value of a temperature. And so the operator just focused on the snack and letting the adjustment of the oil temperature done automatically to be sure that what difference between the traditional and what we develop fryers. This is a comparison of frying oil temperature between with no control and having the control. The first one is without the control. The second one is with the control. You can see in this area for simple one that with the control, we get the temperature of the oil less fluctuation. And for our survey, for the 14 SME, generally they use the raw pork skin about 60 to 800 kilogram a day, and they use 3 or 4 hours a day to prepare the raw pork skin, and 2 or 3 hours a day to fry the product. And they work 5 or 6 days a week. This is the data of using LPG of each SME we visited. We compare it. We compare the using LPG of them. We found that about 21% of LPG can be saved if they use our developed fryer. With this number of saving, in general case, a pork skin producer, let's say they have 100 kilogram a day of raw pork skin, and they can buy like 0.8 US dollar per kilogram of the LPG. By this number, they will save the money for about 450 US dollar in 1 year. So if we sell the fire at 2,700 US dollar, the owner who buy our fire will have 6 years of payback. Even though this number is quite big, for a large production or with subsidy, it can be much smaller. So by now we can I can conclude that our developed fire appear to work very well. acceptable operation and safe in LPG consumption. Academically, the employment of the LPG burner controller at SB offer more precise process control, improve fuel economies, and energy efficiency for small and micro-size food processing enterprises. And in this work, we wish to thank the Fund for Energy Conservation Promotion, Chiang Mai University. This work is a part of a project Industry 4.0 for SME grant by the European Union Horizon 2020 Research and Innovation Program under MSCA, and also thank staff from Faculty of Engineering, Chiang Mai University. And yes, thank you for your attention.
Okay, thank you. Thank you. Any question? Okay. Any question? Your presentation make me hungry, a little hungry. Okay, of course, we just have our lunch. Okay. Any question? Okay, if no question, yeah. Okay, so
anyway, thank you again. Yeah.
Okay, let's go to the next speaker. Miss Pisuwa.
Yes, I am.
Yeah.
Okay.
It works. It works. No problem.
Okay. Okay, good afternoon, everyone. My name is Conduction. Come to presentation. Today, I would like to talk about the investigation on the absorption mechanism of sulfur impregnated catalyst for desalination from waste cable using pyrolysis process. Okay, my outline is present today. The first introduction, the second material and method, the third result and discussion, the fourth conclusion. So this is introduction. Electronic waste or e-waste has become an environmental issue in recent years due to the high metal and flame retardant in e-waste. The main components of flame retardant was hydrogen compounds, brominated chlorinated compound. The hydrogen compound was converted to dioxide at high temperature. Improper treatment of e-waste microbes, environmental problems such as waste cable. The characteristics of waste cable is usually made from polyvinyl chloride or PVC. The PVC can be considered as a fire retardant because it contains chloride. Therefore, the special recycling technology are required to handle e-waste. The pyrolysis process is an interesting alternative technology because it can transform e-waste to many products, including oil, char, and gas. Raw material. The raw material sample was cable. Waste cable. The sample were cut into 6 mm diameter and 3 length. Looking at the table 1, you can see waste cable analysis. The analysis of the cable is post-made, ultimate. The ultimate analysis can be found chloride at on 17% by weight. Catalyst preparation. The conventional catalyst was white silicide. The sulfur loading in white silicide was performed by weight impregnated method with 1, 5, and 10% by weight of sulfur loading in catalyst. Firstly, white silicide in 10 grams and sulfuric acid was mixed in dionyl water. Then mixed catalyst was alive under condition 35 Celsius and 400 revolution per minute for 20 minutes. As you see from the picture, show this one, the original white silicide, and this one, white silicide impregnated floating sulfur is washed dried at 100 Celsius for 24 hours for moisture removal. Catalytic pyrolysis process. Input of these experiments consists 50 grams of the raw material and 10 grams of the catalyst. The operating temperature was 500 Celsius and 50 Celsius per mean heating rate under nitrogen atmosphere. The holding time of process was 1 hour. This picture analysis method analysis, proximate analysis, ultimate analysis, PET, XRF, XRD, SEM, EDF, and the last one is ion chromatography or ICEP. Result and discussion. Catalytic catalyst characterization. Looking at the table 2, you can see the catalyst characterization. Orthosulfur generally can be absorbed in the white silicide catalyst. The BET sulfate and porosity of catalyst were negligible different by 1% sulfur additive. However, the additive of 5 and 10% of sulfur in white silicide catalyst gave impact on BET sulfate pore volume and average pore. The BET sulfate and pore volume of 10% sulfur white silicide were significantly grown by the overfill sulfur in white silicide catalyst. The major chemical composition of sulfur white silicide was sulfur, silica, and alumina ion. It's minus by XRF. The silica and alumina ion was the majority of original white silicide composition. As you can see from the picture, the standard diffraction diagram of white silicide catalyst was for the size structure. The structure of white silicide was not changed after the sulfur impregnation. The sulfur impregnation reduces the diffractogram P by sulfur in infiltration into the catalyst structure. Okay, this picture shows product yield. Product yield are such as product char and product pyrolysis char and pyrolysis oil. Looking at the table 3, you can see yield of pyrolysis product. It was while that the amount of pyrolysis char was high, while the amount of pyrolysis oil was relatively low. Generally, the main component of waste cable was polyvinyl chloride or PVC. The decomposition of PVC was cycled. It mentions two-stage process. The first decomposition step was taking around 300 Celsius, and the second decomposition step was taking around 470 Celsius. The white solid catalyst taking at hydrocarbon compound due to the high acidity, so the polymer was decomposed compound in waste cable. In addition, the sulfuric acid increased acidity in white solid catalyst. Therefore, sulfur white solid was more effective than the conventional white solid catalyst. Okay, this picture shows characteristics of pyrolysis char. This picture shows more theoretical structure of pyrolysis char and the surface of picture A. Thermal pyrolysis char was the most homogeneous and smoothest. Picture B, white solid, and picture C, 1% sulfur white solid more catalyte. Picture D, 5% sulfur white solid. Its surface was slightly flat compared to that of the white solid, and 1% sulfur white solid. And the last one is picture E, 10% sulfur white solid. The catalyst structure on the surface of the char was coarse and merged with the surface. Therefore, the higher sulfur content clearly affected the surface characteristics of the product char. Mechanism of desalination process. For white solid catalyst, the chlorine yield in pyrolysis char was increased by thermal pyrolysis because the white solid was high porosity and strong acidity. Their characteristics of white solid enhance chloride ion capture and the cracking of organochlorinated compound in pyrolysis oil. And in case of the loading sulfur white solid to catalyst, the chloride ion capture of sulfur white solid catalyst was higher than that of white solid because of hydrocarbon in the water metal captured by sulfur dioxide in catalyst and reacted to chlorosulfuric acid. As following question 1. In this one, the mechanism of white solid in 10% sulfur white solid was the chloride ion cracking and capturing constantly In this case, the caking rate of 10% sulfur rate catalyst was greatly higher than the capture rate of the sulfur dioxide. In addition, the 10% sulfur rate was the lower porosity and PET sulfur area. Therefore, 10% sulfur rate could not absorb all chloride content in the volatile matter. This conclusion, the result shows that the amount of pyrolysis oil is low by amount of pyrolysis charge is high by vegetable pyrolysis. The pyrolysis charge component was carbon, silica, calcium, titanium, and aluminum ion. The yield of chloride in pyrolysis oil was 2.98 to 11.47% by weight of total chloride content. The 10% sulfur rate performed the highest effectiveness of chloride removal for the maximum of removal of chloride content in pyrolysis oil was 61% by weight from total chloride content in the pyrolysis oil with 5% sulfur rate. The rate between 5 and 10 of sulfur impregnations was recommended the maximum process efficiency. Thank you for attention. Do you have any question?
Okay, thank you, Miss Pizuan. Thank you for the presentation. Okay, I think it's a good work. Yeah, it's a good work. I have one question. Do you have absorption curve? Do you get an absorption curve for different catalyst absorption curve?
So I stop it here.
Did you carry out this book about absorption curve? You know
what?
Absorption curve. Okay, for catalyst.
Absorption for catalyst.
Absorption curve.
มี absorption curve ไหมครับกราฟการ absorption ครับ
ไม่มีค่ะ I'm not curve absorption of catalyst, so sorry.
Okay.
Do you correct data in the kinetic or in the static?
Data.
How to measure the chlorine after you do the experiment?
The chlorine is the catalyst YCRI impregnate sample YCRI can remove chlorine in the product.
ใช้เวลานานแค่ไหนในการทดลองครับหมายถึงว่าทดลองเป็น kinetic หรือว่าทดลองเป็น batch ครับ
ทดลองเป็น kinetic ค่ะอาจารย์
ทดลอง kinetic แล้วไม่มีกราฟ kinetic นะครับที่ professor ถามครับมีครับมีกราฟ kinetic ไหมครับ
ไม่มีค่ะ
มีแต่ข้อมูลสุดท้ายที่ณเวลาหนึ่งถูกไหมครับ
ใช่ค่ะ
ครับตอบช่วยตอบ professor ด้วยครับใช้เวลานานแค่ไหนในการทดลองครับ
8 months of the test. 8 months of the test. The product is taking YCRI and and testing catalyst preparation to send
Okay, Miss Pizuan, because of time limitation, okay, maybe we can discuss it after the, okay? And yeah,
okay,
this section, okay. So, thank you. Let's go to the third presentation of this section. Mr. Kaumaha Wong. Sorry. Yeah, it's a girl. Yeah.
Yeah, I am Senya Chong Hao Wong.
Senya Kamaharo. Okay.
Yeah.
Please share your screen. Okay. Thank you. Not Mr. It's a girl. Why this here is Mr. Okay. Okay. Sorry?
Sorry, we cannot hear.
No. Yeah. We can say it, but we can hear it. We cannot hear it. Please turn on your microphone. We cannot hear you.
Hello everyone, my name is Selinya Keo Mahawong. I am a master degree student in Energy Engineering program, Faculty of Engineering, Conductivity University in Thailand. Today I would like to present my work, Optimization of Low Temperature Torrefaction for Rice Flour Upgrading. The outline of my presentation are introduction, methodology, results, and conclusion as seen on this slide. So let's start with introduction. Increasing in population and technology have resulted in high energy demand. Renewable energy resources have thus down much attention as alternative energy resources. Biomasses are agricultural waste left in the field and sometimes are burned before the net comes. This biomass can be utilized as alternative fuel in biomass power plants. Rice straw is one of promising biomass, particularly in Thailand. It is considered as well left in the field after harvesting periods and mostly burn casting smoky and PM 2.5 product in the windy city. That rice straw utilization is of interest. Moreover, as it has low fuel characteristics, it is also required to improve its quality for the ease of storing and efficient combustion. Therefore, upgrading rice straw by a thermochemical process called torrefaction is of interest. It is a process using a temperature range of 200 to 300 degrees Celsius under air absence environment for removing moisture content and live volatile matter from the rice straw. Nevertheless, as under low temperature, the main production is commonly in solid phase and called torrefied biomass. Torrefied biomass has low moisture content and low oxygen per carbon and hydrogen per carbon ratios, resulting in higher heating value. Moreover, fiber mass can improve killability and resistance of biological degradation. And this slide is about methodology. Rice straw was prepared by cutting into 2.5 centimeter pieces. Then high heating value was examined as illustrated in table 1. The instrument that used in the experiment is a big bed reactor. It is made of stainless steel, having 50 mm outside the meter and 1000 mm length. The temperature were measured and controlled by K-type thermocouple and proportional integral derivative temperature controller. 15 grams of rice straw were fed into the reactor. After that, feeding nitrogen gas at 5 mm per minute at the beginning until a set temperature will reach. Then the flow rate was reduced to 200 mm per minute during the reaction time. The experiments were planned by central composite design between 200 to 300 degrees Celsius. Reaction time 25.7 to 54.3 minutes. The heating rate was set at 5 degrees Celsius per minute. Data correction includes mass, high heating value, and electrical energy for calculation of energy yield and specific energy consumption. The temperature and reaction time are shown in table 2. Each run was repeated 3 times and the results were evaluated. Mass yield and energy densification ratio can be calculated from in equation 1 and 2 as shown in this line. The torrefaction was optimized by using energy yield and specific energy consumption during the process and determined by equation 3 and 4. For optimization, energy yield and specific energy consumption are considered as the main factor to obtain and optimize temperature and time for the best rice straw torrefaction. As you see in figure 6, the torrefied rice straw and some selected conditions were illustrated. It was obviously seen the difference of appearance. The color of rice straw became darker when using higher temperature and longer time. Table 3 shows the mass yield, higher high heating value, energy densification ratio, energy yield, electrical energy, and specific energy consumption for the 13 runs designed by CCD. It was found mass yield varying from 35.98% and 86.24%. It was reported that torrefaction gave biomass valorization because of molecular reduction and decomposition of hemicellulose. An increase in temperature and time resulted in lower mass yield and higher high heating value. As seen in table, the energy densification ratio was risen from 111.5% to 147.1% when the temperature was increased from 200 to 300 degrees Celsius for 40 minutes reaction time. This indicated that the quality of rice straw was improved by 11.5% to 47.1%. The energy yield of torrefied rice straw ranged from 52.91% to 96.16%. It was obvious that higher temperature would result in lower energy yield. The decrease can be explained by the thermal decomposition of rice straw. In optimization, not only energy yield but also the specific energy consumption was considered. This was because the specific energy consumption indicated the energy used during the process per a unit of torrefied product, which was practical for economic point of view. It can be said that optimized condition was obtained at high energy yield and low specific energy consumption. This led to conclusion that there were two effective optimized conditions which gave high energy yield and low specific energy consumption. Firstly, 200 degrees Celsius 40 minutes, and secondly at 215 degrees Celsius 30 minutes. As shown in figure 7, it can be said that high temperature and longer reaction time resulted in high energy consumption. But let's make you, this gave high specific energy consumption, which is not suggested that the high heating value and energy densification ratio were high. It's worth noting that not only high heating value, but also mass yield must be considered for torrefaction optimization. In deferred brightstone was upgraded by torrefaction. Low temperature torrefaction was produced while reaction time was varied. The temperature and time varying at 200 to 300 degrees Celsius and 25.7 to 54.3 minutes respectively. Based on the results, it was finally concluded that the highest energy yield of 96.16% and lowest specific energy consumption for 23.73 watt-hour per gram were achieved at 200 degrees Celsius and 40 minutes, while the second best energy yield and specific energy consumption by 94.06% and 25.5 watt-hour per gram, respectively, were obtained at 215 degrees Celsius, 30 minutes. Thus, these two conditions were suggested for brightstone upgraded via torrefaction. The research team would like to thank Department of Mechanical Engineering, Faculty of Engineering, and Center of Alternative Energy Research and Development, Conduction University for supporting our work. Our authors are as follows: Ms. Sirinya Keo Mahawong, Assistant Professor Dr. Walinapai Sethanaput, and Professor Dr. Thanakon Bongpatana Sathian. Thank you for your attention.
Okay. Okay, thank you. Any question?
I have one question. In the reactor, do you use any initial gas, such as nitrogen or other gas, in the experiment?
Use nitrogen gas.
Do you vary the nitrogen flow or not? Or fix it?
No vary nitrogen gas.
You use only one condition of nitrogen gas, right? And in the conclusion, the suitable temperature that you show is come from the energy, right? 215 degrees Celsius. That the suitable temperature is come from the specific energy used for the torrefaction, right?
ขออนุญาตตอบเป็นภาษาไทยได้ไหมคะ
ถามว่า condition ที่ 215 องศาครับมาจากcondition ที่ specific energy ใช่ไหมครับที่มันต่ำสุดใช่ไหม
215ใช่ไหมคะ
ครับ
ค่ะมาจากenergy yield ที่สูงลำดับรองลงมาค่ะแล้วก็ specific energy consumption ที่ต่ำรองลงมาจาก200องศาเซลเซียสเวลา40นาทีค่ะ
ครับ thank you
Okay. The next, okay, this section, okay, Professor Tanazit, it's your turn to chair. I have
okay.
ask.
Okay.
Okay. Thank you.
The next one is weapon ID 89. Mr. Ying Li, right?
Yes, it's me.
Please share your screen and
Okay.
start.
Can you see my screen? Hello, can you see my screen?
Yeah, we can see it, but
Okay.
your sound is quite
Sorry.
just speak louder, speak louder. Yeah.
Okay. Good afternoon, everyone. My name is Ying Li from the University of Nottingham in China. Today, I'd like to give a presentation about the experimental study on the thermal contact resistance of the thermoelectric generator. My presentation.
Please speak loudly. Would you please speak loudly? I
Okay.
cannot hear you clearly.
How about now?
No, not good.
Oh, then I may wear my earphone. Wait a minute, please.
Can you say it again?
How about now?
Better.
Better?
It's okay, I think. Yeah.
Okay, I will try to speak louder.
Yeah.
My presentation will include 4 parts. Introduction, experimental work, results and the discussions, and lastly, the conclusions. As we all know, we are depleting energy, and the energy crisis is becoming worse and worse in the last few decades. According to the statistics from our world in data, the world energy consumption is increasing all the time, among which the consumption of fossil fuel, which includes coal, oil, and gas, has been making up the largest part for decades, and it is still going up year by year. The latest number in 2019 shows that about 84% of the world's energy was supplied by fossil fuel. As we know, with the consumption of fossil fuel, normally CO2 emissions and the heat are generated. But the efficiency of using fossil fuel is quite low, with a large part of its energy dissipated through waste heat. So we may wonder whether there is a method to recover the wasted heat, or at least recover part of it. Fortunately, we do have such a potential technology, which is called Thermoelectric Generator. The Thermoelectric Generator is also called TG for short. It is a technology that can transfer heat directly into electricity. The working principle of the TG is shown on the animation on the left. A TG module, as shown on the right, consists of several thermoelectric couples connected thermally in parallel and electrically in series. The main advantage of the TG is that it has no moving parts, so it is noise-free, reliable, and compacted. Besides, as it has no emission, it is environmentally friendly. The TG has been widely used in various applications, including aerospace, solar energy, ocean energy, automobiles, households, and wearable equipment, and so on. However, a wider application of the TG technology is limited by its low conversion efficiency. Studies have shown that in order to have a larger conversion efficiency and power output, a higher temperature difference between the hot side and the cold side of the TEG module should be maintained. There are several aspects influencing this temperature difference. One of the important aspects is the thermal contact resistance existing between two different materials. The thermal contact resistance plays a vital role in the TEG structure and the geometry optimization and its performance. Therefore, in order to get the accurate value of the thermal contact resistances in a TEG system, an experimental test rig was designed. This is the schematic diagram of the test rig. The tested TEG module used in the experiment is shown in this picture, which is made by Segre in China. Thermal grease with a thermal conductivity of 6 is applied on the hot and cold surface of the TEG module. The experimental system consists of 4 subsystems, that is the heating system, the cooling system, the temperature measuring system, and the load temperature system and the load pressure system. The temperature at different locations are measured by the temperature measuring system, and the heat flux through the TEG system is calculated by these measured temperatures. The data processing is given on the right. The heat flux into the TEG module is calculated by the temperature measured in the alumina block, which is between the heat source and the hot side surface of the TEG module. The thermal resistance of different layers in the TEG module, including the ceramic layer, the copper layer, and the T legs, are calculated by these equations, where the subscript I refers to the different materials. Combining the heat flux, the temperature measured, and the calculated thermal resistance of different materials in the TEG system, the thermal contact resistances can be derived. With our test rig, 3 different thermal contact resistances at different locations in the system are measured. That includes the thermal contact resistance on the hot side, on the cold side, and inside the module. The total thermal contact resistance is the sum of the 3. The experiment reviews the impact of the heat source temperature and the load pressure on the TCR respectively. The TCRs at various heat source temperatures under different load pressure are given in these charts. The first chart on the upper left illustrates the total TCR. It can be seen that the total TCR is in magnitude of 10 minus 4. The second chart on the upper right describes the variations of external TCRs and the internal TCRs, from which we can see that the external TCR is the main contribution to the total TCR, and the internal TCR is in the magnitude of 10 minus 5. The charts on the bottom respectively give detailed information on the TCRs on the hot side and cold side and the internal TCR. It can be concluded that both the external and internal TCRs go up with the increase of heat source temperature. The 4 charts here shows the influence of load pressure on the thermal contact resistances. From the results, we can see that all the TCRs decrease generally with the increase of load pressure. The impact of load pressure on the TCR is more significant when the heat source temperature is low. So, from our experiment, some important conclusions can be made. The main conclusions are listed here. The value of different TCRs can be obtained. It should be noted that the pressure on TCR is much more significant at relatively low heat source temperatures. The external TCR on the hot side is always larger than its counterpart on the cold side. From our experiment, we can see that the load pressure play a vital role influencing the TCRs and the performance of TEG system. Therefore, when a TG module is installed, the load pressure is an important consideration to pursue a lower thermal contact resistance and thus achieving better performance. So that's all for my talk. If you have any questions or suggestions, please feel free to discuss with me. Thank you.
Thank you, Ms. Yingling. Any question? Very good presentation. Any question?
I have one question. Okay. I think the work is interesting, and it is shown that the load pressure is significant.
Yes.
On TCR. Yeah. Let's and you give more details about the numbers of TCR, the quantities of TCR, magnitude of TCR is different pressure. My question is, in the equipment, what is the range of pressure? Or the range of pressure, the scope of pressure in the reality of equipment?
Okay. The pressure we tested in our experiment, the largest is 1,200 kilopascal. But if you further increase the pressure and the thermal contact resistance will decrease further, but the degree of the decrease maybe not that large.
Your pressure scope. You please
My pressure scope.
turn to the page of conclusion. Please turn to the page of conclusion. Yeah,
Okay.
we see that you can change the pressure range from more than 200.
Yeah, 200 and.
What is the real range? The real range. What is the real range in the TEG system?
I understand your question.
Yeah.
It varies from different systems because normally we install the TG module in a system with heat source and the cooling and the heat sink. If you apply different pressures, and that will present different performance. It depends on it's different from system to system.
Okay.
Thank you.
Thank you.
May I ask a question?
Yes, please.
Yeah. Thank you very much. So thanks for the good presentation. The question is about, have you seen any effect of the mechanical pressure that you're changing on the TEG, on the mechanical structural stability or the mechanical stability of the thermoelectric cells? By changing the pressure, do you see any loss of electrical contacts or any other mechanical damage to the thermoelectric cells?
Yes, we do see some mechanical damage on the TG module because the ceramic layer in the TG module is quite fragile. If the pressure is very large, it may be broken. So that is a difficult question.
But there's no damage to the electrical contacts?
The electrical contact will
inside the P and N junctions.
Increase. Yes, if the TEG module is broken, the thermal contact resistance will increase largely.
So I think maybe I advise the extension of this research could be finding an optimum operational pressure where you get the best minimum contact resistance, but still it's mechanically strong, mechanically stable. Okay.
Yes.
Good.
Thank you for
Thank
your
you.
suggestion.
Any question? Okay, no more question. Thank you, Ms. Ying Li, for your good presentation and answer. For the next presentation is number 114. Mr. Ravi. Are you here, Mr. Ravi? Okay, Mr. Ravi.
Oh, I'm here. Good afternoon. Thank you, Professor Thanachit. And good afternoon, everyone. Thank you for attending this presentation with me. Today, I'm going to talk about, my name is Ravi Koirala, and I'm a PhD student at RMIT University, Melbourne. And my presentation here is about my PhD research. Basically, a part of it on active vapor transfer and condensation of eductor for freshwater production. So majorly, we're talking about eductor and freshwater production, that's desalination process. So a quick background on what we are going to talk. We're going to talk about the basic background on where the research lies and what was the methods we implemented for the study, and some of the major peak point research outcomes from the activities that was performed. So a quick background is, as we are well aware that we have global issues, a global rising problem due to urbanization and different other factors. The stress of water is increasing every day. And in other hand, when we talk about industrial applications based upon mechanical sectors or heat implementation sectors, there are large amount of heats that are being wasted in the industrial sectors, or let's say low-grade heats are being wasted, either that's from industries or from solar sources. So this project has been, this activity was carried out with an aim of collecting or bringing together two different problems from two different sectors in order to reach to a common solution or a sustainable solution for producing fresh water. So where the saline water or salty water, as we are well aware that most of our Earth surface are covered with it, can be desalinated by using these low-grade waste heats, and a sustainable water production process can be developed. So on the basis of problems, there are some opportunities to solve some of the future challenges on energy efficiency and water crisis. So basically, thermal desalination means it's a freshwater production process where salts are separated from salty water or sea waters or any other brine water or any other waste waters. And there are basically two kinds of processes. One is thermal and another is mechanical processes. So when we talk about mechanical processes, they consume although they are very simple, but they consume very large amount of energy. Whereas when we talk about thermal desalination processes, they can produce a relatively higher amount of water. And these are three basic water production processes that are largely implemented in industries or on off-grid systems. So, but the thing is, they will need very large vacuum operation systems, and also will need large condenser systems, as they are thermally operated, where they vaporize the water vapor, and then later they condense these vapors for production of fresh water. So our project lies in addressing these two challenges, where large requirement of large vacuum pumps and requirement of large condensers will be replaced by a simple mechanical device called eductor, which can simplify the overall operation of this thermal desalination process. So what are eductors? So eductor ejectors are the simple mechanical device that operates on the principle of conversion of velocity energy to pressure energy. So here our primary fluid motive liquid water flows through this, where energy conversion occurs, And at this region, a low pressure zone is created due to the conversion of kinetic energy into potential energy. And due to the pressure difference between the atmospheric condition or wherever the vapor is generated and the internal pressure difference here, the vapor transfers or transport inside the system, where this vapor, when mixes with this liquid water jet, then it condenses and a single phase or liquid water comes out. So this thing runs in a loop. And then of water condensation occurs, or this thing can act as both water condenser and a pumping device or pumping unit. And the performance of these kind of devices are measured in terms of entrainment ratio, which is the ratio of suction mass flow rate by primary mass flow rates. So what are we going to talk about? So basically eductors for vacuum generation. So vacuum generation and vapor transfer, where experimental and computational studies, what are the experimental and computational study was done, and what were the objective of these two studies. One was for flow phenomena study, then what is the application, how it will be implied in desalination process, and after implication, if there was any challenges, or how would we mitigate those challenges by doing some design modifications. So these three parts were addressed here. So basically, ANSYS fluent-based CFD solver was used to do some computational analysis. So this is domain. So it's an axial domain, just to show the dimension, but the analysis was performed in three dimensions. And this is the basic boundary conditions, where primary flow was inlet fresh water at 25 degrees Celsius, and the secondary flow, the suction flow, was water vapor at 95 degrees Celsius. So corresponding saturation pressure was given as the boundary condition at this case. So, and there was the outlet condition. So, and the experimental study was performed with this rig here. This is the experimental setup with pumps, pressure tanks. This is the experimental specimen with eductor or ejector that we are talking about. And there were two other samples of eductors, which we also studied, where we tried to see the condensation phenomena within the eductor by doing the experiments. And there's some tank, a vapor generation system. So, this is the basic primary result, where we are talking about the capacity of eductor to be implemented in water desalination process. The first criteria is the capacity to create a sub-atmospheric pressure conditions. So we can see that with increasing primary pressures, the absolute pressure, the absolute suction pressure is decreasing, and experimentally we were able to achieve up to 40 kPa absolute pressures on those eductors, the eductor that was experimented. And when we talk about vapor transferred capacity of vapor transfer within the eductor, we could achieve, we could see efficiency of around up to 12% at different back pressure conditions. When we did the experiments, we could measure the efficiency up to 12% for these eductors when they are actually pumping. So this is maximum vacuum generation capacity, and this is the maximum pumping capacity, or let's say maximum efficiency for pumping. And when additionally, the computational study also was just done to see how the flow visualization, or what is the mass transfer phenomena within the eductor. And we see that of vapor coming inside, and this is the jet of water going in. And we see that there is interphase interaction at the interface of this liquid water and vapor, and at the outlet, all the vapors that gets into, it's trapped in, or it's condensed, and liquid water goes out of the system. So this ensures that, okay, eductor is capable of vacuum generation and condensing within its system. So this was another study that was performed for flow visualization to see what is the mechanism of this mass transfer. And we could see that over the period of time, this region of complete condensation oscillates between this suction chamber. This is the region and the throat of this eductor. And we could see that this oscillation phenomena was repetitive when the experiment was done. So the application of this eductor for the applied process, that is for water desalination process. So eductor, this is a desalination membrane desalination module, that's vacuum membrane distillation module, where eductor is implied. Electric eductor is connected to its permeate side or its vacuum chamber, where the saline water, hot saline water that has been heated through this heater circulates in this loop. And through this membrane boundary, transmembrane boundary, the vapor are transferred towards this permeate chamber, and then the eductor, the pumping action of eductor sucks this vapor into the system, and hence the whole process runs in loop, and the freshwater production occurs. So in order to maintain the constant inlet temperature, a chilling system was installed for our experiment, but different other alternatives like underground heat exchangers can be implied when we are talking about off-grid water desalination units of this kind. So this was the experimental setup that was actually used, the chiller, the experimental setup, the eductor that was implied for this particular experiment, and the data acquisition systems. And the experiment was done with PTFE membrane with the feed concentration of 11 grams per liter of salt concentration, and the feed temperature of this water was 80 degrees Celsius. So the result of this was we got a promising result compared to the existing systems of these kinds, where we could get water of up to 43 kg per meter square per hour when we operated the system. And so from we could see that this pink line here is the mass flux, and the green line here is the pressure at that particular condition on those suction chambers. So it is creating a sub-atmospheric pressure condition on the inlet suction tube, which is ensuring that vapor would go in, or there would be enough amount of vapor pressure difference to drive the vapor inside the eductor. So so we could see that there was promising result, but it was not enough equivalent to the current vacuum membrane distillation process, although the process was very largely simplified. So we thought what could be the reason. So we did some exergy analysis to see where maximum amount of exergy was being destroyed. And we could see that the last maximum amount of exergy destruction was occurring on this region, where the vapor and the liquid comes in contact with each other. So what we did was we modified this region by increasing the interface interaction area with 2 nozzles and 3 nozzles. So so that we could increase the interface interaction area by 1.7 times and 1.4 times and 1.7 times here. And this is the result, the computational result we see, where there is larger mass transfer and happening in the system. And this in turn also increased the thermal performance of these eductors. And that we can see here, the 3 nozzles has significantly large entrainment ratio compared to 1 and 2 nozzle systems. So this also shows that there is more potential of having higher performance of the system in desalination units. So summarizing this result, we could when we study the performance, we could see that eductors are capable of generating the vacuum as well as functioning as an isolated condenser unit for water desalination systems, and we could achieve a result up to 43 kg per meter square per hour. And in order to, there are some potentials to enhance this mass flux by increasing the mass transfer rate, by increasing interface interaction area, by increasing the number of nozzles in the eductor. So in terms of energy and power summary, what we have explored here is we have explored a simple mechanical device which can replace the bulky vacuum pumps and condensers in off-grid water desalination units. And this can significantly reduce the footprints of existing vacuum membrane distillation system, and also will simplify these systems in future implications of these projects. These are references that I used for the presentation. Thank you so much.
Thank you. Very good presentation. Mr. Ravi. Any question from the floor? Any question? Okay, I have one question
Yes.
about in the conclusion that you have said that the optimization of the design, you use the exergy destruction, right?
Yes.
How about the energy? Have you used with the energy and exergy destruction together for the optimization, or only the exergy destruction?
So actually, for optimization part, what we only focused at that point was only exergy destruction. So where in which of these regions, just highlight that point. So we did the exergy analysis for each of these sections. We found the exergy for each of these points on this eductor and just compared where maximum amount of exergy was destroyed. That was the only thing that was done actually from because we wanted to enhance the thermal performance of the system, or that's just enhance the mass transfer rate within the system.
Okay, thank you for your answer. Any question? Okay, we come to the last paper of this session. Is number 96. Number 96 is Mr. Lee Mo Siang. Are you there? Are you here, Mr. Lee?
Yes. Can you hear me?
Okay, please.
Yeah. Please wait a minute. Can you see the screen? Sorry. Can you see the PowerPoint?
Oh, yes. You can hear and see your PowerPoint.
So maybe I can start my presentation.
Yes, please.
Good afternoon, everyone. I'm very honored having the chance to give my presentation to you. My name is Lü Haoxiang, and I come from University of Science and Technology, Beijing. My presentation topic is study on sodium nitrate doped with graphene nanosheets, heat transport characteristics, and mechanism. My presentation can be divided into 5 main sections: backgrounds, materials and models, phase change characteristics, thermal conductivity, and lastly, conclusions and prospect. As we all know, renewable energy exists the fatal flaw of intermittence and fluctuation. This has created a need for energy storage. Molten salt phase change materials are favored by people because of their low cost, good thermal performance, and good compatibility. However, the low thermal conductivity has limited their application. In order to improve their performance, a lot of work has been done to improve the thermal conductivity. Organic shell, high thermal conductivity skeleton, and the introduction of high thermal conductivity particles. Among the 3 main methods, nanoparticle computers has the obvious advantage for their simple preparation process. Small number of particles can significantly improve the thermal conductivity. The particle usually has a high thermal conductivity with a size of 1 to 100 nanometers. However, the thermal conductivity of the computers is significantly improved by carbon-based nanoparticles, while decreased by alumina nanoparticles. In addition, the phase change enthalpy and specific heat also show contradictory decreasing or increasing trends. In this paper, we hope to explain the contradictory results through our work and seek the optimal doping ratio of nanosheet particles. Sodium nitrate, an important component of solar salt, was selected as the phase change material. Graphene nanosheets was selected as the nano-reinforcer. The phase change characteristics and the thermal conductivity of the composite was tested experimentally, and the mechanism was further discussed by molecular dynamics simulation. The wet method preparation process of the composite materials was selected as shown in the figure. Samples of 0.5 to 3% samples of 0.5 to 3% doping ratio were prepared in order to explore the influence of the GNS doping ratio on the phase change thermal characteristics. As you can see, sodium nitrate supercell structure was established by introducing holes, and the reliability was verified by comparing the simulation results and experimental results of the density at 773 Kelvin. GNS was randomly introduced into the sodium nitrate structure model to simulate the random distribution of the nanoparticles. The surface morphology of the composite materials was characterized firstly by scanning electron microscopy. As you can see, sodium nitrate clusters appear close to the nanosheets as the GNS doping ratio increases. At the same time, the adhesion force at different positions on the surface of the composites was measured by atomic force microscopy. As can be seen from the figure, the adhesion at the interface of GNS and sodium nitrate is obviously stronger than other positions, which means that strong force field exists at the interface. The melting point and the latent heat are as follows. As can be seen from the figure, the melting point of the composite decreased slightly, yet the phase change enthalpy decreased significantly. Interestingly, we found that the phase change enthalpy has a non-colligative decrease. The lowest phase change enthalpy appears with a doping ratio of 1.5%. To visualize the change in enthalpy, we defined the crystallization efficiency theta. As shown in the figure, theta of all the composites are lower than 100%. The lowest value appears when the doping ratio is 1.5%, which is only 86%. We further observed the behavior of sodium nitrate close to GNS. It can be seen that the dense layer of sodium nitrate close to the nanosheet, and they do not participate in melting process. Mean space displacement can reflect the intensity of particle motion. It can be seen from the figure that MSD gradually increases at 300 Kelvin. We believed that GNS weakened the interaction between the internal molecules of sodium nitrate, leading to the increased atomic mobility as well as the intermolecular collision frequency. Thus, the melting point decreased. Meanwhile, the interaction energy between GNS and the sodium nitrate was calculated. As the doping ratio increases, the change trend of the interaction energy is exactly the opposite of the phase change enthalpy. It is obvious that the non-colligative change of the interaction energy leads to the change of the phase change enthalpy. To account for the above change in interaction energy, the atomic position distribution of the composite was calculated by taking GNS as the origin. We can see that there is a sodium nitrate dense layer of 2 to 4 angstrom. Besides, the centroid equivalent distance between the dense layer and GNS increases with the doping ratio. Considering that the interaction force between GNS and the sodium nitrate is only van der Waals force described by the Lennard-Jones force field, as the distance increases, the attraction between the two will first increase and then decrease for sure. As for the thermal conductivity, the thermal diffusivity of the composite was measured firstly by laser flash at room temperature. Then the thermal conductivity was calculated by following equation. Apparently, the thermal conductivity of the composites was significantly improved, an increase of 245% with 3% doping ratio, achieving a breakthrough in the order of magnitude. Here, we try to explain the increase of thermal conductivity from a macroscopic perspective, the vibration density of the atoms before and after compounding was studied. It is obvious that the main vibration peaks of sodium nitrate cover a wider range of intermediate and low frequencies with GNS doped, showing a wide range of overlap with GNS. This means that phonon vibrations between the two match better, which indicates a higher thermal conductivity. The contribution of phonon vibration in different frequency to the thermal conductivity was calculated. It can be seen that the contribution of low and intermediate frequency phonon vibration increases after compounding. This indicates that GNS stimulates more intermediate and low frequency phonon vibrations inside sodium nitrate, which accounts for the increased thermal conductivity too. Besides, we quantitatively calculate the overlapping phonon energy of GNS and sodium nitrate before and after compounding. The larger overlapping energy, the more harmonious vibration between the two materials. You can see the overlapping energy of GNS and sodium nitrate is significantly higher after compounding. So we can see that the improvement of the thermal conductivity of the composite material seems to be attributed to the vibration matching of GNS and sodium nitrate. The above is all the content of this paper. In general, our conclusions are as follows. The difference of the interaction force between GNS and sodium nitrate under different thickness of sodium nitrate dense layer results in the non-colligative reduction of enthalpy. The high thermal conductivity of GNS and phonon vibration matching between GNS and sodium nitrate are the main reasons for the significant improvement of thermal conductivity. And the 1% doping ratio has the best performance in maintaining the phase change enthalpy and has achieved a 113% increase in thermal conductivity compared with other doping ratio. As for the prospects, firstly, we intend to investigate the effects of nano-reinforcer types on thermal conductivity enhancement by comparing the interfacial thermal resistance of different kinds of nanoparticles with sodium nitrate. The calculation model of interfacial thermal resistance is shown in the figure, sandwich structure, and the interfacial thermal resistance can be obtained by applying heat source and heat sink at both ends. The simulation results of the interfacial thermal resistance between GNS and sodium nitrate are shown in the figure. The interfacial thermal resistance between boron nitrate nanosheets and sodium nitrate would be our next step. Besides, the phase change properties and the thermal conductivity of different mass doping ratios would be calculated to seek the best one. That's all of my presentation. Thank you for your attention. I welcome your questions and suggestions.
Oh, thank you. Very good presentation. And any question from the floor?
Lü,
Hey.
yeah, Mr. Lü is my student, so I cannot answer. Maybe I also can answer question, right?
Yeah.
Yeah, okay. I just want to know the error bar. There's a flash apparatus test. Yeah, what is it?
Yeah. Maybe we can add it later. In our paper, maybe we can add the error bar.
Yeah, but no,
Yeah.
do you know how many about? Yeah.
Every data are measured 3 times.
Oh, it is. You know, I know. This is these are average values. Okay.
Yeah.
but the error magnitude, didn't you have it?
We have the data, but I didn't add it on our presentation. Sorry.
Okay. Yeah.
Any question?
I have a question here. Thank you for your presentation. And I have two questions. The first one is about the phase change temperature of your PCM.
Sorry, pardon.
The phase change temperature. I mean,
melting temperature.
Yes, the melting temperature.
The melting temperature of sodium nitrate is 308 degrees C.
At degrees. Okay, thank you. And
Yes,
then I'm wondering the thermal conductivity you've mentioned in your material. Is this thermal conductivity have something to do with the direction of the material? I mean, is it isotropical or anisotropical?
Sorry, to do with what?
Direction of the material. Does it have
定向材料还是非定向？各项同性。
Yeah.
Yeah. Sorry.
It's okay.
The composite is uniform in all directions.
Oh, so the
because the GNS is dispersed in the sodium nitrate randomly, so we can ignore the influence about the direction.
Okay, thank you.
Yeah. Thank you for your question.
Any question? Okay, no more question. Okay, we come to the end of the session. Thank you for the chairman, Professor Yang Hui Feng, and
thank you, Professor Tanazit. Thank you. You too.
And thank you for the host of the ICEP 2021 and everyone for this session. Thank you.
Thank you.
Bye.
Bye.
Goodbye.
Yeah, before we leave, we can have a group photo. Can you please
group photo. Okay.
Can you please turn off on your what's called video camera so that we can see our faces, and then we'll take a photo and then we'll just sign off.
Not adding interior structure of the blade is a limitation, so that's why I have again studied for the structural improvement of the blade.
And
I think
in your evaluation of the annual power generation, you showed equation there.
So thank you very much for your support and help, especially chair and co-chair, and also the participant, and also our organizer people are there and supervisors. Thank you very much, and see you tomorrow at the same time. So we'll have our second day 2.
So actually this is from
Thank
the
you.
level distribution.
Bye.
All right, bye.
This is a graph between the probability distribution function and the principal velocity that I have used during the MATLAB coding.
Okay.